Good morning, everybody. My name is Teraphan, and now I'm going to talk about the site-specific seismic hazard assessment. Though the title, the title over here is the Probabilistic Seismic Hazard Assessment for Metro Manila, but it could be used as an example case for many places around the world that we need this kind of assessment. What is seismic hazard assessment and why it's important? I'm going to explain you through this talk, and then I would explain you also the step to do it, and then how to use it properly, and then what is the innovation that we have improved in the last 10 years about this kind of topic. So as you can see in the picture, here is the seismic hazard assessment for United States, and this one has been developed by USGS, United States Geological Survey. They use this one as a baseline so that the engineer in the US would try to follow, so that they're going to build a structure more safely. And why really we need this map? Because we know that the earthquake is not happening everywhere randomly. We know where it's going to happen, but then when we know where it's going to happen, the engineer would ask again, okay, what is the value that we should decide for? Because if we're going to build the strong building for everywhere in the country, it would be very expensive and very costly. So this kind of picture would show you in the area where it's going to have the high seismic hazard. So the engineer would decide accordingly to that, depending on the rate, how fast it's going to occur. And this is the map that we developed for seismic design code for Thailand. And this one that we developed for Metro Manila. And my presentation content would be like the introduction about the PSSA and the component of the PSSA and the process of the PSA for the example case Metro Manila. So like I said, why we need PSSA and why it's important, because the earthquake hazard is still cannot be predicted in advance. Like we cannot tell you with this exact date, time, hour that it's going to happen. Science cannot do that yet. It doesn't mean that we did not try. We tried, like before the magnitude 6 in United States in 2004, that happened magnitude 6. They invest a lot in trying to putting the instrument all around the active fault. But when the active fault happened, they can before it happened, they can detect nothing. So it means that we invest a lot already to try to understand the earthquake. But science in this for the earthquake is quite young, so we still did not have enough idea how to do it properly. But what we do is we know is where it's going to happen, but we don't know exactly when. Even though we know exactly when it's going to happen, how it can be used, we cannot move our city, we cannot move our infrastructure, dam, power plant, nuclear power plant. So we have to live with it. If you say that someone don't want to live in California because they have a chance of a big earthquake, no, people want to live there. So how are we going to live there properly? We have to know how we're going to decide for. That is the main reason. So the PSSA is the current long-term strategic tool in many countries like United States, Italy, and everywhere in the world that we try to protect our structure from the earthquake. And the PSSA product would be like the map for different storm ground motion parameters. This one would be the term for the engineer, because we know that even for the same ground motion, it would interact differently for the different kind of structure. And then the application of the PSSA would be like, obviously the first one is National Seismic Design Code, and the setting of insurance premium, and the risk and loss assessment study. And I would like to call again, what is the term of the peak ground acceleration? Like this is the ground acceleration that we record in New Zealand for magnitude 6.3 in 2011 Christchurch earthquake that destroyed the whole city. It actually is the magnitude is not quite big, but the ground acceleration is 0.9 g. That is quite big. If I'm an engineer and going to say to you that, okay, in your city you're going to have a chance of 0.9 g, people would say to me, I'm crazy. But if we have this kind of study perform and try to look around our infrastructure, then we will know more in advance before that. So this is the term, the peak ground acceleration, that I'm going to say a lot in this study. Peak ground acceleration is something like when the ground moves, it will be shaking, and the acceleration that can record the peak is called PGA. And then the component of the PSSA study. The component would be, the first step is we have to identify what is our site that we interested, and then we have to identify what is the seismic source that is nearby our site, like the active fault here, and here, or the area source here. So we would have a clear picture where it is, and we're going to decide for that. Because if there is no seismic source near our structure, so we don't have to be worried. And then the second step is we have to define what is the recurrent rate of each seismic source. What is the recurrent rate mean? For example, if this fault F1, they have the big earthquake every 50 years. And this fault, even though it's closer, but it have the big earthquake every 500 years. Which one would be your concern? It would be this one. That's why we have to know what is the recurrent rate of different active fault. And then we know that for this one, the ground shaking, like we know that when you far away from the earthquake, from the epicenter, you will feel it less than when you stay closer to the fault, right? So there is some study, they try to understand this one, and this is the distance, and this is something like peak ground acceleration. So the peak ground acceleration would drop all along the distance. So this formula, we can use it also in the PSHA study. But our understanding of the ground motion is not perfect. Like the dot here that you see is the peak ground acceleration that they record for magnitude 7, for different earthquakes at magnitude 7. And the line here is the one that we use to predict. But you can see that there is a lot of variation. Like at the same location, it could be like 0.4, but another for the same earthquake, and maybe from the same magnitude earthquake, magnitude 7 at the same distance, another one is 2G. So what's wrong with this one? So this means that there is some variation that could be induced by the direction of the propagation of the earthquake to the real structure. Like the earthquake is not just a point, it's just a line. So if you lie in the water pool, you push the water. If you stand in front of the water that you push, then you're going to receive the large peak ground acceleration over there, not at the back. So this is something that we have to take into account, the effect that sometimes magnitude 7, you can, at the same distance, you can have higher peak ground acceleration, sometimes you can have lower acceleration. That we have to take into account our calculation. And then what you're going to get at the end, you're going to get the seismic hazard curve. The seismic hazard curve would, in this y-axis, it shows you the probability of existence. The probability of existence means that the lower the value, it means the less probability that it's going to happen. And then the higher chance that the peak ground acceleration will be. Because the big earthquake not happen every day. It had a cycle, so you did not expect to see that every day. From the same location, it needs some time to accumulate its strength before that big earthquake could happen. So, but for the lower chance here, maybe the earthquake that happen like quite more frequent, like magnitude 4 or 5. Like if you live in the active region, you would expect magnitude 4 or 5 every day, or not every day, something like for 1 year you're going to get like 10 or 20 times for your structure. So your structure should be able to withstand that. And then we're going to design for your structure for the worst case also that is going to happen to your site. This is the whole concept of the PSSA. And like this is the seismic hazard curve that I tell you. So this is, for example, for the 0.3 second spectral acceleration, and this is for the spectral acceleration at 1 second. So for the probability that it's going to be happen at this design level, this is usually they consider as MCE, maximum credible earthquake. They're going to point to the probability here, and then link to the value, and then if you do it for a lot of spectral acceleration that you interest, then you get a curve here. This one we call uniform hazard spectrum. Uniform hazard spectrum means this is the spectrum that tell you that if you want to design the structure to withstand this kind of probability, this is the level that you should design for. And it's going to be depend on what kind of your structure. Like for 1 second, it would be quite long period structure. Like for example, could be like 10-story building, but like 0.3 would be lower, shorter. It's something like 4 or 5-story building. And I just give you another basic, like, so why we have to consider for different spectral acceleration. Because the spectral acceleration is the peak acceleration of representative oscillator. Like this is the ground acceleration, this is your building. If your building is short or small, then it would be controlled by here. But if your building is quite long structure, the tall, it would be controlled by here. But for the tall building, it would be more complicated also, because your structure would have subject to higher mode response, this is here, and then the nonlinear response, that is from the long period ground motion here. So sometimes you have to consider also all the effects that could happen to your structure, like the first mode, second mode, or third mode. And now I'm going to show you the example case that we have been done. Like this one is the Metro Manila. Then we're going to go through the selection of the seismic source, the collection of seismic activity rate, the selection of appropriate ground motion prediction equation, the PSSA result, the aggregation, assessment result consider different soil condition, and conditional mean spectrum, and strong ground motion selection and scaling. Like this is the map. This is the year, and this is the magnitude of the earthquake. We try to understand the rate of the earthquake that's going to happen in Philippines or in Manila. And then we found that from 1900 to 1940, we have just in the database, we have just the magnitude that is larger than 6, because earthquake cannot be detected randomly, but by just the people say that, oh, they felt the earthquake, they need the instrument. And before that time, we don't really have much instrument in this world. That's why just called a big one. This one is a gap. Actually, it happened all around the world, because during that time is the World War II. So the quality of the data is quite reduced. And then you're going to see that after that, 1960, we start to have much better data. Like we start to detect magnitude 5. And then after Philippines, the FIWOC, the representative of the government to detect the earthquake in Philippines, they try to install more stations to detect the earthquake. They can go down to magnitude 3. So now we have the data of what kind of the activity that the earthquake happened in the Philippines. And this one is going to be used in the calculation also. This is like the timeline to show what is the big earthquake that had happened in Philippines, like magnitude 8.3 in the southern Philippines, and this is 7.7 Luzon earthquake. Yeah, the better small magnitude, because of FIWOC, they install more seismic station inside the country. And for the earthquake source, I'm going to separate into the shallow earthquake, intermediate earthquake, and the deep earthquake. Why? Because if the earthquake happens quite very shallow, like less than 50 kilometer depth, you would feel it very strongly. But if the earthquake happened like deeper than that, the effect to the structure would be less. So that's why we have to separate the activity rate for these two. And then we're going to use different like ground motion prediction equation, because from the study of different ground motion that we have been recorded, we found that the ground motion for the deep earthquake and the shallow earthquake is quite different. And this is the seismic city map. This is Manila, and for the red dot is showing you the earthquake that happened all around Manila, and the side of the circle showing you the magnitude of the earthquake. So it means that the activity rate for the last 100 years that we saw is much concentrated here and here. And this is the big active structure Manila Trench. This is the part of the subduction zone. Here also another one is Luzon Trough. And this is another big active fault here that is they call Philippine active fault zone. And the Luzon earthquake happened around here in 1999. And then what we try to do is we try to understand the characteristic of the shallow earthquake in Philippines. Like here we found that the average depth is 25 kilometers because the crustal in Philippines is quite thick. So the earthquake would happen quite a little bit deeper than what we see in like South in Thailand, Myanmar and Vietnam. In Thailand, Vietnam and Myanmar is around 10, or sometimes you can see the surface larger, but here it's quite deeper, around 25. So it's good that it's a little bit deeper, so the energy that propagates to the surface of the ground could be reduced. And then we try to calculate the activity rate here, and this one we're going to use in the model. This showing you that where exactly the activity rate of the earthquake that happen more often than the other. Like if you're going to build your structure here in this island, then you have to be consider that there's a lot of earthquake happen here. So you have to design your structure for the chance that the earthquake will happen frequent more than the one if you're going to design structure somewhere around here, because the activity rate of the earthquake is quite different. And this is the Metro Manila. And like I said, that the characteristic of the deep earthquake, intermediate earthquake, and the shallow earthquake is quite different. So this is like the seismicity of the intermediate earthquake. We can see that now the picture is look different than the shallow one. Now it shift closer to Manila, because this is Manila Trench, this is subduction. So we could see that this is the shallow one, and then it the plate start moving inside the island. So we see that this is the way that the intermediate earthquake you're going to see. And here we would see the lake more here and here, not here. So now we understand better where we should expect more intermediate earthquake near the Manila Trench. You should expect around here and here, not here. And then the average depth here is 70 kilometers. Okay, it's quite good also because it's a little bit deeper. So the chance that the strong ground motion affect your structure would be a little bit reduced. And then this is for the deep earthquake. The deep earthquake means it's deeper than 100 kilometers. Even though it would be less concern, but sometimes it does have some effect to the infrastructure. Like it could, if you did not prepare for it, for the deep earthquake, you know your structure is really bad, it's going to fail anyway. So we want to understand the whole process. So the deep earthquake, you will see, now you see that it becomes closer to the Luzon Island, because this is the subduction zone, so you see it move a little bit further to the east. And for the deep earthquake, you will see much more concentrated here. And this is the activity rate that we compute for the deep earthquake. For the whole Manila Trench, we see that the activity rate is much more here in this zone. So it means that if you in Luzon Island and someone asks you, okay, if you want to design for, if you ask what is the chance that the deep earthquake would happen more, here or here, it would be here. So you would know the recurrent rate of each different seismic source now. Even though we try to get the seismic data like what I showed you previously, but it's just 100 years. And the earthquake is quite complex than that. Before the earthquake would happen, they would need to accumulate their energy before it really happened. Like it would need, sometimes it could be 100 years, 2000 years, we don't know that. But if we know where is the active fault, then we would try to use all the data, try to capture what is the recurrent rate of those. Like this is the map made by fieldwork. So the fieldwork, they try to understand what is the active source, active seismic source in their country. So they draw the line. The red line here is the active fault that they know. And here is the subduction zone here. So this is the basis that we're going to use in the further study. And this is the zooming closer to Manila. Like the red line here is the active fault that we know. So we're going to use in our seismic hazard study also. For the Metro Manila, the big concern is this fault, that is Marikina fault. It's quite close to the city. And then there is some study trying to understand the current rate of this one and how often it will be happen. Like 500 years, 1000 years, 2000 years, it will change a lot. Because if you want to design the structure like going to be very important and you need it to be able to withstand the big earthquake. For example, if this one really happen, then you have to have a better idea what you should decide for this one. And how we going to estimate the magnitude of this one? We're going to estimate by the empirical relationship. This one is, there's some study that try to understand that, okay, if the magnitude 7 happen, what is the rupture length that could be? Like for the rupture length of around 80 kilometer or 90 kilometer, it could be something like 7.3. And the longer the rupture length, the larger the earthquake could be. For example, that could be very clear to you, like 2004 earthquake, Sumatra earthquake, magnitude 9.2. That one is, the rupture length is around 1,200 kilometers. But for like magnitude 6.8 in Myanmar in 2011, that one is 40 kilometers. So you will see that the larger the rupture length, the larger the magnitude that would happen. And this kind of data, they're based on different the earthquake that already happened in the past. So we quite certain with the number that could happen. But what we're not certain is Marikina earthquake going to produce magnitude 6 or 7 in the future. We don't know. But we know that if it really rupture for the whole length, it could be around 7 also. And this is, I just want to show you the earthquake database that they have compiled in order to develop this equation. Like from the United States, this earthquake magnitude 8.3, also 7.8, the rupture length is around 300 kilometers. But like magnitude 6.5, also 6.8 here, 51 kilometers. So it's quite different. So the longer that it could be happen, then the larger the earthquake magnitude that you should expect. Then after we got what is the largest magnitude that could happen from the active fault, then what we need to know another one is what is the recurrent rate, how fast it would happen, how many years that we will see that. So this kind of information we need the help from geologists. They're going to dig to the trench near the active fault, and then they're going to see what is the movement of that. Something like if they see there is 5 earthquakes happen from the same fault, and each of them have the different recurrent time. Like each fault happen, each earthquake happen every 500 years. So we're going to assume that maybe the big earthquake from that active fault going to happen in every 500 years. And then if, for example, you're in the middle of the circle, so maybe there's the likely chance that you would not see it in another 200 years, something like that. But if we see there is a certain evidence, it happens more frequent every 50 years, and then now it's 20 or 30 years past, so you should expect that you should build the structure more stronger to resist that kind of the earthquake that could happen in the 20 years or so. And this is like the active fault, and this is Metro Manila, and then this is the location of the site that we have to consider for the site-specific hazard assessment. And this one, I want to show you the cross-section of the subduction zone in Manila Trench. This is the depth, and this is for the latitude 15 to 16. You will see clearly this is the subduction zone. You see this is the shallow earthquake, and then it starts to drop down. Another one here from 14 to 15, and Manila is here. You will see that it's here. And for latitude 13 to 14, you will see here another subduction zone. But these three is quite different in the sense that this one is the dip is dropped faster. Dip is quite different than the one in the north. So it has interpretation for our calculation, because for the subduction zone, this is for the example of the Chilean type, the two plates collide to each other, then it will be subduction zone. And then because the two plates coming to each other, it will be the compression. This one you could expect a big earthquake like magnitude 8 or above. But what we see here, this is not a compression. So what we see here is like it pulled down, it has been pulled down. So it's not a compression, it's a tension. So from the statistic and from our understanding, it's a tension, it's not compression. So we would expect less big earthquake from here. It could be something like 7.5, but it should not create a great earthquake like 8.5, 9. So understand this concept. You would know what is the seismic source near your structure, and then you're going to design accordingly to that. If not, you're going to overestimate your design value. So this one is quite more closely to Manila, and then we are quite lucky. And then after that, now I'm start to perform the calculation. I'm going to separate the shallow earthquake, intermediate earthquake, and the deep earthquake by using different ground motion prediction equation. And then I'm going to consider the crustal fault, the one that we have some information that how fast it's going to happen in 100 or 500 years, 2000 years. And then I'm going to consider for the subduction zone, Manila Trench. I separate into the northern segment and the southern segment, and then the eastern Luzon trough. And this is the seismic hazard map for Metro Manila for the 43-year return period. For the 43-year return period, it means that what is the value that you should expect the earthquake that could be happen quite frequent, and it would be concentrated here and here, and it would be from here, and it fits well with what we observe for the frequent seismicity map here. So we observe that the frequent earthquake that happened in the last 100 years, it fall around here. So it's, sorry that is quite zoom in, so you would expect random earthquake happen from this zone of the Manila. That's why this value is become high in the in the eastern side. And then when we go for the 425 year, we start to see that the earthquake effect from the western molecular fault start to appear. It's because we know that it's there, and we from the paleoseismological study, the scientists, the geologists went to the field, they dig the trench, see how fast it happened, and then this is going to have a result in our estimation. So it means that if you're going to design a building for the 500 years, some consideration should be considered for molecular fault. It doesn't mean that it's going to be magnitude 7. It could be like something 6.5 or 6, and then it happened very near. Then you have to consider that your structure should be able to withstand that. And then for this one for 2,475 years, now the peak ground acceleration becomes stronger just near the fault, because like I said previously that you would expect the last peak ground acceleration near the fault, and then it start to drop down further. So the one that is located close to the fault, you should be able to design your structure better than the one near the shoreline or the Manila Bay. But in the Manila Bay, maybe there is some other kind of problem, something like liquefaction, because if the big, it doesn't need to be that big, but if you have a sand and then sand layer, and then there is some ground shaking, then the ground would change from the solid to the liquid, because the water start to coming out, and then you will see the liquefaction. The liquefaction then would make the soil become less strength to accommodate the weight of the structure, and then you start to see that your foundation has collapsed. So there is some kind of different kind of consideration based on your site that you can use to construct your structure. And then we also prepare the map for different spectral acceleration, like that one previously I showed is peak acceleration. But if your structure is a little bit more longer period, like 0.2, this is the map. And then 0.2 for 475 years, and 0.2 for 2,475 years. And this is one for 1 second for 43-year return period. And this is 1 second for 475 years, or the DBE, design basic earthquake. And this one 1 second for the 2,475 years, or the MCE, maximum credible earthquake. So you will see that it would more concentrate here near the fault, but then it start to drop down. And when we look back again for the location of the considered site, then we're going to prepare the uniform hazard spectrum for each site. For example, now I'm going to shoot for this one. Like for this one, this is the uniform hazard spectrum for the current site. Then we can determine the value from the period 0, that is peak ground acceleration, until 10 seconds. And this value is going to different from one to each other, because we expect that the length of the occurrence would be different. The value is quite high. I also believe that it's quite high, because the site is 400 meters from the fault. So if it really happened, your structure should be able to withstand that. So what I'm trying to say here is the value is high for a reason. And after we know that what is the value that we should decide for, then another question is from the engineer. When they're going to decide, they want to say, okay, now we want to select the ground motion for the value that we specify for each return period, where it's going to come from. Like for the 43-year return period, for the peak ground acceleration, where it's going to come from. So we perform the de-aggregation. De-aggregation is the process to see what is the highest probability that the earthquake could come from that return period. Like for peak ground acceleration at 43-year return period. The bar here is going to show you what is the probability that it's going to have larger than the author. And the color is going to show you about the magnitude of the earthquake that happened. So for the 43 years, for our site here, Metro Manila, and the probability that's going to happen is going to, from the random earthquake, happen farther north to the site, magnitude around 6.7 at 63 kilometer distance from the site. Then the engineer would know, okay, this is the earthquake that we should decide for, if it's going to happen. And this is the one for 2,425 years. Now it would be more clear near the site that is the other one is not important, but the important one is the fault. That is Marikina fault. The height of the bar is quite high. And from the aggregation result, we found that the magnitude that we should expect is around 7.3 to 6.8 at 400 meters from the site. And then we can determine also for, like, if your structure is really long period, like 5 seconds. 5 seconds would be very tall structure, like 50-story building. So what is the earthquake that you should decide for, where the effect would be from? So it's still the active fault near the site, because if it magnitude 7, it would produce the long period ground motion, and then we should expect from the same site also, like 7.3 at 400 meter earthquake, 400 meter distance. And this is the result of the de-aggregation from different spectral acceleration. This is from 0, 0.2, 0.5, 1, 2, 3, 5, 7.5, and 10. And the magnitude and the distance and the site to source azimuth is quite unique that for this location, most of it at the 2% probability of accident in 50 years, or the maximum credible earthquake. The Marikina active fault seems to be the one that controls the whole length that engineering interest. So when we're going to select the strong ground motion for design of this structure, we're going to select according to this one, because this is the one that controls the seismic hazard in our interest site. And then when we know that it's quite close to our structure, then we have another problem, because, like I said, if you push the water in the water tube, when you push it further to you, then you will see the large impact. But if you, like at the back, you will not see the large impact. That's what we call the pulse. Then you should design structure differently. But the thing is, currently we do not have clear data where it's going to rupture. Marikina fault going to rupture to the north or to the south. We don't know that yet. Then the further study of the Marikina fault would give us a better idea what scenario we should expect. But for the time being, we're going to consider from what we try to understand. Like for the selection of the ground motion, we following the International Building Code, that is ASCE 705 also. They say that each ground motion shall consist of the horizontal acceleration history select from an actual record event. So, like I said, that in the past they have some seismic station that is recorded really close to the earthquake. So then they prefer to use that one, because there's some technique that they can simulate the ground motion also, but sometimes it's also subjective. So they recommend that try to use the actual one that we have been seeing, and then obtain from the record event having the magnitude, the fall distance, and source mechanism consistent with those that control the maximum considered earthquake. It means that if you're going to select those records, you should select from the one that should really happen to your structure. near the site. Like the Marikina fault is strike slip fault, so the way the movement would be just in the horizontal way. If you remember in the Chichi earthquake in 1999, magnitude 7.6, that one is thrust, so there would be the vertical movement also. That would be also quite difficult to deal with for the vertical movement. But luckily, Marikina fault is just strike slip. So what we have to deal for is the horizontal movement. Yeah, the fault distance is also another thing that we have to keep in mind, because some of our site is very close to the fault. If it really going to happen, then we will see differently if we select the ground motion for 50 or 1 kilometer far from the fault. You will see it quite different for example, the near fault pulse. And then when the required ground motion are not available, appropriate simulated ground motion shall be used. Well, this one is just for the option, but mostly we're going to follow this one. And then the ground motion shall be scaled such that the average value of the 5% dam response spectra for the source of the motion is not less than the design response spectrum. It means that when we have the uniform hazard spectrum, we have the rough idea what is the value that we should decide for. But earthquake ground motion is quite complicated than that. Sometimes when we record is lower than that, maybe there's some effect that we don't know. So in the code they tend to be more conservative. They say that should not be less than that. From 0.2 T1 to 1.5 T1. T1 is the first mode of your structure. So they would like to keep the design response spectrum within the length of your first mode response. And then if at least 7 ground motion are analyzed, the design member force are permitted to be taken respectively as the average of the value determined from the analysis. Because as you will see in the next slide, from the select ground motion there would be some variation. Because the earthquake ground motion is quite complex sign. Even we describe it the same magnitude 7, sometimes it would produce different ground motion, like I said you previously, that maybe because the direction of the fault, is it going to be at the front or at the back. Sometimes like the magnitude 9 in Tohoku earthquake, that one the larger length is just 500 kilometers. But for the magnitude 9.2, the Sumatra earthquake in 2004, that larger length is 1,200 kilometers. And those two are different in the larger length, and different larger length would have different result, because for the Sumatra earthquake, they have a larger length, they're going to produce larger energy at the long period. But for Tohoku earthquake, they're going to generate more high frequency seismic wave because it's shorter. So this is the thing that the sign of the earthquake we don't really know. That magnitude 7, if it's going to happen, it's going to be more than the statistic that we have. It would be longer or shorter than that. That's why they say take the average, because we still don't know the full understand of the Marikina fault. And this is how we're going to select. This is the target spectrum, the black one. And what you're seeing here, the blue and the green here, is the ground motion that it has been recorded real time. After we select like magnitude 7 from the same distance, we try to scale it to match with the target spectrum. And from 7 record, and here's the average, the red one here. The vertical here, I'm sorry, this is the vertical ground motion. The vertical ground motion is most likely to be less than the horizontal one. And here's the ground motion that we select and scale to our case. You will see that even if from the same magnitude and the distance that we try to select, you will see that the seismic wave is different. This one is contain more long period ground motion because you can see it going up and down, but this one is more different. You see the peak and then it drop down quite fast. That's why I say that even in the ground motion, the peak ground acceleration, they also have some different, like this one is 1G, maybe this one is, okay, this one is 0.5G, but later on we would going to make it fit to this one. But if the ground motion have this one would be more damage to your structure. Why? Because it's subject to longer ground shaking. But this one it peak very fast and then it drop down. So this is the complex process of the earthquake. If it's going to happen, it will stop very fast or it stop not so fast. This is the reason that they want us to select different ground motion into analysis. Because we want to capture the variation of the variety of the ground motion that could happen to the site. And this process maybe you know already, like when we know the earthquake ground motion, we're going to perform the nonlinear structural model, the dynamic equilibrium structural response, and then we're going to get maximum intensity industrial drift ratio. And this is, for example, if you're following the code, an example of the building code type, you will see that the black one, that is the target spectrum, and the record spectrum is the one from 7 record ground motion that we try to fit with it. And then this is the maximum industrial drift ratio for the left, for the y direction, and the ground motion set number 1, 2, 3, 4. For each set of the number, we're going to have like something from the code would be 7. And then you're going to have different maximum industrial drift ratio. And then you take the average, 1, 2, 3, 4. You will see that if the set number 4 is the one that did not really consider the method that I has been explained previously, like they choose randomly different magnitude, different distance, and then different source mechanism. So the variation would be there. So that's why it's important, like the set one that is the one that considered like the more closely from what we understand that's going to happen to our side. So you will see that the difference would be there. If you choose randomly, did not consider what is going to really to happen to your structure. This is going to affect to structural analysis that you're going to design also. That's why they write very clear in the code. If you want to select the ground motion, you should choose the one that's going to really happen to your structure. If magnitude 7, okay, select the one near magnitude 7. If it's very close, okay, select the one very close. And also for the same focal mechanism that is going to happen also. And the next generation, like it's not, in engineering we also have the improvement in our analysis also. Then in United States now there is a term that they usually use, usually made it term as next generation analysis. They made the next generation for everything, like the new aircraft, there's a next generation aircraft. Then they call this one as a performance-based engineering. And what is going to be changed is that they know that the uniform hazard spectrum that they got is quite high. It's quite high because that one is considered for the different kind of earthquake that could happen. Like from spectral acceleration at 1 second, it could be from the magnitude 6 at 50 kilometer distance, but for magnitude for spectral acceleration at 5 seconds, it could be from magnitude 8 at farther away. So they understand now that they should consider for the spectrum acceleration at single period only, the one that mean to your structure. and then more careful consideration of the ground motion probability to be consistent with the result of the PSSA. And a greater number of dynamic structural analysis need to be more acceptable. Like this is what I want to say. Like this is the uniform hazard spectrum. This is the example of the United States, USGS. They say that at the site of Riverside, California, the uniform spectrum of the 2%, that is the MCE, is the red one. And this is the result of the de-aggregation. They say that the magnitude that should happen is 7, the distance is 12, the epsilon is 2. So when they plot it, this one is magnitude 7, the distance is 12, it's much lower than that. And when they plot the epsilon, the one that they're going to describe the variability of the ground motion, is just here. So it means that uniform hazard spectrum is the overestimation of what they see from the result of the de-aggregation. So this is the one that we're going to consider, because the uniform hazard spectrum consider all the earthquakes that could happen to your structure, and that might not be happen. So this is the new concept. They're going to use this one instead of the red one. So it would be more perfect match with your structure at 1 second. For example, if your structure is, the first mode is at 1 second. So this is the one that we're going to design for. So we're not going to put a lot of structural demand to our structure if we put to the red one. And like I'm coming back to the de-aggregation analysis for my site in Metro Manila for true probability of existence in 50 years. For example, if I'm going to consider for spectral acceleration at 2 seconds, I'm going to choose more closely with this one. But the thing is, the Metro Manila is the Manila fault is quite very strong effect to mostly all the structural period. Then it would be, it control all the structural period that we consider. But anyway, it's going, if we use this concept, it's going to be less than uniform hazard spectrum. Another thing that I want to say is that when you're going to select the response spectrum and consider the conditional mean spectrum, so what is the epsilon that I said previously? That is 2. The 2 is mean that, for example, this is the ground motion for magnitude 7 at distance like 10 kilometers. If the epsilon is high at this period, it means that we're going to see the positive peak here. But if it's negative epsilon, it would be drop down here. So it means that you did not expect to have the large epsilon for the whole length. It will be just this one that has a peak. So the effect of the epsilon would be clear if it would be positive or the negative one. Then that's going to affect in the way that you design your structure also. And this is the uniform hazard spectrum and the conditional mean spectrum for the 409 short site. This is the uniform hazard spectrum for the blue one, and then the CMS at 5.7 seconds. For this one, we know that the first mode of this structure is allowed here, and this is the conditional mean spectrum, which is here. It's much lower than the uniform hazard spectrum, because we know that our structure is here, and the effect that we should expect from the result of the de-aggregation, it should be allowed here. So it means that if we design like this one, we did not use uniform hazard spectrum, we're going to reduce the effect of the earthquake from magnitude 7 that's going to happen here, close to our structure, and then we're going to use this one in our structural analysis. With this one, you're going to maybe overestimate the spectrum of your structure at higher mode. And then from the code of the Tall Building Initiative, TBI, they said also that for this one, you have to consider also the second mode and the third mode of your structure. So the second mode here is 1.7. So we fit with it at around 1.7, and here is the conditional mean spectrum for 1.7 second, and the third mode is 0.7, which is around here. So we're going to select the ground motion and scale it to match with all these three, and then we try to check if our structure can perform better. Actually, it would give our structure less demand for different kind of scenario that we're going to face for the earthquake. Uniform hazard spectrum for 2% would be too high. It would oscillate your structure at all periods at the same time, more than long period motion also. And now, when we perform the site-specific seismic hazard assessment, the other thing that we should consider also, so what is the site that we're going to construct our building? Is it going to be rock? Is it going to be soil? It's going to have an effect to our ground motion. Like this is the ground motion record in acceleration time history record at two sites in California from 1989 Loma Prieta earthquake. This record in the rock, on the rock side, and this one is record on the steep soil, and both record from the same distance, like 22 kilometers approximately. And if you look here, it's not much different, right? The time is more or less look like the same. This is the east-west, this is the north-south, this is the vertical direction. Well, if you look at the response spectrum, it would be different. This one from the rock, this one from the soil. So you will see that if you structure this situated on the soil side, you will see the amplification here at 1 or 2 seconds. Compared to here, this is 1-2 seconds is quite low. This is what we call the side effect. Side effect because the soil is quite soft, then it would amplify. It's just like you put a jelly in your hand and then you shake it. The jelly would have larger amplification than the one when you shake your hand. Then you will see that here at the long period for the soil, you should expect something that's going to be larger if you compare to the rock. And also when the ground shaking is become large, there would be nonlinear side amplification, and then the peak ground acceleration for the soil would be lower than the one for the rock. Because the ground cannot amplify all the ground motion, it's going to have some limit. There would be the damping and would be lower here for the short period, but it will be larger in the long period. And the long period is the one with the tall building, high-rise building that we face in all around the world. Because we tend to build our structure near the river, then this is the problem for every big city in the world, like Bangkok, Manila, and Los Angeles. You should expect something like this side amplification effect. And this one for the spectral velocity, you will see more clear. Spectral velocity here for the rock, and this is for the soil. It's quite different. Here for the soil, you will see that it has a high spectrum at the long period, quite clear. And for the one that I showed to you previously for the map of the Metro Manila, that is computed based on the bedrock. But if I want to consider for different soil type, like in the NEHRP network, they set the different kind of soil classification, like soil type B, C, D. They would separate like based on the shear wave velocity. Like if it's very soft, it would be SD. And if it's SC, it would be a little bit steeper. But it doesn't mean that all would be in this value, because this is just a rough estimation. We don't know, okay, here, is it soil type SB, SC, SD? I don't know. Then we need the data from the site, like the borehole profile. Or then we have to measure like the shear wave velocity measurement at the site. There are many different methods that we can use, like measure of the surface wave, MASW, the SPT, or the recent one is the micro tumor array analysis. And this one for the seismic hazard also for the spectrum at 1 second for different soil conditions. This one is for soil SC, this one for soil SD, and you will see that here the chart also different. And you would not expect that it's going to be high forever, that the value would not affect. It would not amplify. There is a theory that the soil would not amplify like linearly, because when the ground shaking quite strong, there would be non-linear soil amplification effect. Then the desired ground motion would be a little bit lower. And this is the method that I said, the micro tumor array analysis. This one is quite cheap. You did not have to perform the borehole study. Mostly the borehole would cost you quite a lot also, and it could not go that deep. Like they said that the VS30 means the shear wave velocity until 30 meters. But why they set as 30 meters? Because that one is the farthest that the borehole profile can be drilled within 1 day. That's why the concept of the VS30 comes from. And that one is quite easy also. But if you imagine your structure is very high-rise building, right? 40-story structure. And if you just know the velocity profile of your structure just 30 meters, is it going to explain anything? No. So for the site-specific, that your site is very important. You want to know more. What is the condition underground, and how to do that quite less expensive. You're not going to do borehole profile for like 1 kilometer, right? This is the method that currently we have been using in Bangkok also. It could go down to 1 kilometer to measure the shear wave velocity in the ground. So we would know more what is the condition on the ground that we're facing, and then we're going to perform the ground response analysis, because we know more about the ground, what is really going to happen, and then we can model it more better idea. This is the one they're going to put the instrument here, and then they're going to put another 3 all around, and then they're going to measure the noise at the same time. And then when they start to separate from each other, they're going to measure the noise, and then going to be better know what is the shear wave velocity underneath. Like this one is around 5 meters, so they can measure the shear wave velocity around 5 meters. But when, like this is the study they performed in central Bangkok, in Chulalongkorn. So here they start from here, and another 3 here, and then they start to separate from each other. The farther that they go, the longer the measurement that they can make. From our analysis here, we can go down to 1 kilometer. And we know that the Bangkok is not the soft soil is not just 30 meters. We know that it's a basin, and it goes until from the Gulf of Thailand until here also in Phnom Penh. Because in the past, this land is not a land, it's a bay. With this method, we can see very clear where is the structure of our basin, and then we can model the ground response analysis more clearly than previously that we do like just a borehole profile. And this one, like I said, it's going to measure the noise nearby, and then they're going to measure at the same time. When they separate from each other, they're going to go down further underneath of the soil. Then we're going to measure better the shear wave velocity. This study is going to be used when we have the basin effect, like the Bangkok itself, and I think in many countries, in many cities also, because we tend to build our city near the near the river, that is going to have the basin effect. And I think that might be all for me. If you have any question, if I speak too fast, I'm sorry, but I would be more than happy to answer. Thank you.
Factor to make the average one. So once you select those 7 factors, it's just random, or you have to measure the core characteristic of the considered fault line, or is there any ground to how to not select 7?
This is good question, because from time to time when we going to select this one, we going to have a lot of questions from our engineer also, how to select it properly. Like I said, that what we going to select the ground motion for the design of our building, we must know where is the seismic source. Like if your structure is here, you're not going to select the earthquake that's going to happen like 7 kilometers far from your fault. You're going to select here, like this one would be a little bit longer distance, and also the magnitude is also the matter, because it's going to have the effect. And because like I said to you that there is the complication when you near the fault. Because if your fault is moving northward here, you're going to see the directive effect, that is the pulse. And then if your structure is, for example, here, then there might be a chance that it's going to fall larger northward. Because the earthquake is not just a point. When it's going to happen, it's going to, like, it would start maybe propagate here and go there. So another thing that you could consider is the azimuth where it's go from the earthquake to your site. If we have better data from this active fault, okay, where it's going to happen, it's going to rupture from the south to the north or north to the south. It's going to change a lot, because your structure would be here, then maybe it will start here to here. We need more data from this active fault, then we're going to be better select the ground motion for consider of our site. Another thing is also for the soil site. If it's going to be soil site S, class SC, it's going to have different amplification, like I tell you. For the rock, the ground amplification would not be that much because it's rock, but the soil would be amplified in a long period. Like in this project, we have the borehole profile for these 2 sites, and it's rock. So the effect of the long period ground motion, it would not be that much compared to the area around here. So that's why when we perform the site-specific hazard assessment, we want to know everything: the location of the site, the location of the source of the seismic, and then the activity rate is going to happen, and the soil profile. Everything. So because we want to know what is going to happen to our structure, and then it should be able to withstand it. And what is the condition of our site, something like that. Here is rock, so the spectrum of the long period is lower than the one is here. That is the main reason. So we have to consider everything. If there is evidence that further study and show that evidence that okay, this zone is, there would be the segment. This one is not going to be magnitude more than 7, and it would be more around here. So the value would be very low here, but not here, something like that. But based on the current data, we have to assume the whole thing uniform, because we did not really have enough data, and also it's in the metro city. It's quite difficult to go down and try to dig the trend to see where is the active fault movement. So it's quite challenging for this one.